Hi guys, welcome to God Academy. In this lesson, I'll be taking you through impedance. So how to calculate the impedance of an AC circuit, right? In our previous lesson, we went through phasor diagrams and also how to calculate sinusoidal voltages and currents with the wave equation. So we continue with impedance. And the impedance, we're looking at the three types of impedance, the R, the XL, and the XC, which is the capacitive and the inductive reactances, right? Okay. So first of all, let's look at R. In any DC or just a simple linear circuit, right? If I have my resistor connected this way and a current flowing through a branch, right? The voltage across this resistance, right, is given as Vm sine omega t. So this is a general. Omega is your angular frequency. Is that not it? Okay. So here to find your current flowing through this branch is simply giving us what? Your V over R. Simple Ohm's theorem, right? You can see the V and the I, they are just in the same phase. So my current then becomes Vm sine omega t over R. And therefore my current is simply C. Vm over R gives me my Im sine omega t. So from here, I'll say that I have my I and I have my what? My V well defined. Is that not it? Yes. But so here I can say that my Im, which is my peak current, is always equal to my peak voltage over the resistance. This is one thing you should put in your mind. Okay. Then also if my Im is equal to I so if I want to find the RMS, right? So generally know that RMS here. So my I RMS is simply equal to the Im over square root of what? 2. As simple as possible. So here, once you know this, that's all. You know how to represent your I generally as Im sine omega t. Then you can relate Im and Vm, find your RMS. So here we say that our current and our voltages are in the same phase. Okay, they are in the same phase. They are not. There is no difference in their phases. And our interest here is that we found that our resistance R here and the connection between Im and Vm. So just put this one in your mind. Now let's move to a circuit which is having an inductor. So this one is just a current through a resistor, right? So let's go to a current in an inductor and let's see the relationship between the current and the voltage. So now inductor is a circuit element which we didn't talk about in the DC because it's applicable in the AC. Okay, so it works creating magnetic field in its core. So an inductor is something like this, a coil, just a coil around any solid material. Once current passes through, a magnetic field is created within this coil and it is purposely used for magnetization, whether in memories or in transformers or whatever, right? Now, what is our point of interest? So let me draw a branch having an inductor connected. The current is flowing through this branch and let's see what happens here. Let me introduce a polarity here. The voltage across this inductor. In our previous lessons, at the beginning of the applied electricity, you realize that I wrote a formula that the voltage across an inductor is generally related as your inductance times the change in the current with respect to time. Generally, there is a formula. So you realize that the current through an inductor is not fixed. The change in current due to AC, please take note, the change in current in an inductor due to the AC nature, the alternating nature of the current creates a magnetic field. So for us to find an instantaneous voltage, we need to differentiate with respect to that particular time we want to find the voltage. Then we multiply it by our inductance. That is all. What is our point of interest here? So here you know that generally our I in an AC is equal to our peak current sine omega t. Is that not it? So let's solve for our voltage. So using differentiation, our V is simply equal to what? Our Im here. So see the L. The L will come out. My Im will come. Remember that omega will come out when you are doing differentiation. Sine omega, then cosine omega t. Remember this simple differentiation, right? So once you differentiate, you realize that you get this. We don't need cos, we want to represent it in sine or standards. So V now becomes omega L Im sine omega t plus 90. And this is very important thing in applied electricity. So we say that the voltage across an inductor leads the current by what, 90 degrees, or you can other way say that the current lags the voltage by what, by 90 degrees, as simple as that. So here we can say that our Vm, so see, this is our voltage, is that not it? But you know that generally the wave equation says that we should have our peak voltage attached to the sign. Therefore, my Vm, which is the peak voltage, is generally equal to here, the omega L Im, if you clearly remember. So this whole thing is representing our peak voltage. So we can equate the peak voltage as omega L Im. Is that not it? Period. Once you have this, then what's next? We are looking out for the impedance. Okay, the impedance. I have my peak voltage here, right? So using the RMS, you know that my V is equal to Vm over what, square root of 2. Is that not it? So I have omega L Im over square root of 2. And this gives me omega Li. We normally use the RMS in our calculation. So now this is our the RMS, the voltage in RMS, as simple as possible. Once you have V relating omega Li, then I can say that my V over I is simply equal to omega L. And this is what we call capacitive, I'm sorry, this is what we call reactive inductance, okay? So it's a form of impedance. Here we don't use resistance, we call it reactance. So it is called XL. XL is simply equal to omega L. So this is where the formula is stemming from. Please take note of this formula. We'll be using it along the way. So omega L is our inductive reactance, right? Which is the resistance due to the inductance in an inductor, as simple as possible. So having looked at this, you can see that the voltage is leading the current by 90 degrees. Current is lagging by 90. For every current through an inductor, it is fixed. Now let's move to current through a capacitor. That will be the so current in a capacitor. So a current in a capacitor, what happens for a current in a capacitor? So I'll take a branch with a capacitor, the current flowing through I, my capacitance polarized plus minus V. So generally, you know that a current flowing through a capacitor is given as the change in the voltage across the capacitance times the capacitance. This is the general formula. And as you know that the voltage in any AC is given as Vm sine omega t, is that not it? Therefore, to find my change in voltage over time, I'll have my C outside as a constant, my omega will come, is that not it? Then Vm cos omega t. So my I then becomes omega C Vm, then sine and cos are related by 90, okay? They are complementary in nature. So if I want to represent it in sine, it becomes omega t plus 90 degrees. As simple as that. Okay, so sine is leading cos by 90. At this point here, you can say that the current is now leading the voltage by what, 90 degrees. So in a capacitor, the current rather leads the voltage by 90. Okay, so you can say that my Im, right? Sorry, my Im is simply equal to omega CVM from here, because if this is your standard wave equation, then everything attached to the sign is your what? Peak current. So my peak current is simply omega times capacitance times what? Vm. I need to find the RMS form. So my RMS, which is Im over square root of, will give me omega CVM over square root of 2. And that simply gives me omega CV. Okay. So if my I is giving me omega CV, then my resistance, which is V over I, is simply going to give me 1 over omega C. Therefore, my capacitive reactance XC is equal to 1 over omega C. Okay, so my capacitive reactance is 1 over omega C. And these are the reactance and the resistance you have looked at so far, right? So take note of them as you'll be using it to calculate our impedance. Now, let's analyze some few circuits. The first circuit is what you call RC circuit, or resistor to capacitor circuit. If I have a resistor and a capacitor in the same circuit, how do I analyze it? So let me draw a model equation with an alternating source here, V. Okay, I have my resistor in series with my capacitor. Okay, nicely here. Here, the voltage across the capacitor is VL, the voltage across the resistor is VR. So if I'm to analyze this, you know that by KVL, Kirchhoff's law, the total voltage V is equal to my VR plus what? VL. Is that not it? In a vector form. Okay. So here, my V squared should be equal to VR squared plus L squared. But this can be derived from the phasor diagram. Remember that in a capacitor, the current is leading the voltage. Okay, so I have my I and I have my voltage, and it's 90 degrees. But remember that VR, which is the voltage across a resistor, is always in phase with the current. So VR will fall on this. So VR will rather fall on this. So I have my VR and I have my V, which is my VC. Okay, sorry, this is VC. Therefore, to find my effective or total voltage V, which is here, it will lie here. Then this will be the difference, phase difference. Okay, so here you can see what you can see here. So I have my VC here, I have my VR. So using Pythagoras theorem, that's what you can see. The effective voltage become V squared equal VR squared plus VL squared. Now let me use the capacitance approach. So V is the same as I times our impedance, right? All squared. VR is simply I times R squared, everything all squared. Then VL, which is, sorry, VC, I'm supposed to use C. We are dealing with capacitance, right? So my VC is simply equal to my capacitive reactance times my current, all squared. Therefore, I can take I away because it's appearing everywhere. So therefore, Z squared is equal to R squared plus XC squared. And I will say that my Z is equal to the square root of R squared plus XC squared. So for you to find the effective impedance in any RC circuit is simply the square root of the sum of the squares of R and not XC, as simple as possible. Let's check the phase difference. The phase difference theta is simply equal to tan inverse of what? X. Yeah, so it's VC over R. So XC over what? My R. But here, the phase difference is not 90. Whenever you have R and C, the phase difference is not 90. It could be less than 90, right? So, but it will not be more than 90. That is it. So take note of this expression for every RC circuit. Let's analyze an RL circuit. So for an RL circuit, we call it resistance to what? Inductance circuit. So I have a resistance, my resistor here in series with an inductor, right? An inductor. So connected to an alternating source, my V, my VR, then my VL. As simple as that. Remember, in an inductor, the voltage rather leads the current by 90 degrees. So 90 I and V. Okay. So therefore, and remember that my current and my voltage across resistor is always in phase. So my VR is always here. As simple as that. So I take my effective voltage here, then I introduce my phase difference here. So my VR appears here. Therefore, my V is simply equal to V squared equals VR squared plus VL squared. As simple as that. So this is my VL, okay? My VL squared. Remember IZ all squared. This is impedance times, but this one is IR all squared plus I times what? XL all squared. I goes away, my Z is simply equal to the square root of R squared plus XL squared. As simple as that. The phase difference as well, theta or phi here, is giving us tan inverse of what? XL over R. Here too, it is not 90, it's less than 90. Okay. So let's finally analyze what you call RLC circuit. In an RLC circuit, I have resistance, I have my inductance, and I have my capacitance all together, right? So my resistor will come here, in series with my reactance, in series with my capacitor, right? As simple as that. Connected to an alternating source here, my current flowing through I. Simple as that. So in an RLC circuit, remember we have three V's: voltage across R, voltage across L, and voltage across C. So my total voltage in the vector form equals the sum of voltage VR plus VL plus VC, right? Let's represent this using the Phasor diagram. So remember that my voltage is leading in my inductance, right? My voltage is lagging in my VC. My current is here, I, and my VR is in phase. So here I can see that my VL and my D, they are opposite. So I can combine them here as VL minus what VC. Then we use this part of our circuit, right? Nicely done. So at this point, I have my phase difference here, and I'm interested in only this section of the circuit because I have found the effective. So now VC goes away, right? The down one goes away, we clear it. So this is what you're left with. So with this expression, I'll say that my V squared is equal to what? VL minus VC all squared is now together plus VR squared at this point. So here to I times Z all squared equal to VL, which is what? IXL minus IXC all squared plus RI all squared. So at this point, I can go. If you simplify, you see equals square root of what? XL minus XC all squared plus R squared. This is what we call inductance and the impedance of an RLC circuit. Get to know this formula. We'll be using it along the way. As well as our theta is now equal to tan inverse of what? XL minus XC over what? R. Therefore, the angle will differ but will not be 90. Let's solve an example for you to understand all that I've been calculating. So looking at this example 1, a coil has R 12 ohms and an inductance L which is equal to 0.1 henries. It is connected across 100 volts 50 hertz supply. Calculate E, the reactance and impedance of the coil. B, the current. Then C, they are calculating for the phase difference. So this is a very simple question here, and it is an AC circuit, okay? A coil has a resistance of 12 ohms and an inductance of 0.1 henries and is connected across 100 volts 50 hertz supply. You have to calculate the reactance and the impedance. So impedance, then the reactance, and the current as well as the phase difference. If I'm to model this, my coil will be here, then the L, which is 0.1, and my R, which is 12 ohms. So now let's see. To calculate the reactance, the only reactance we have in our circuit is what we call the inductive reactance, XL, given us what? Omega L, which is 2 pi FL. Is that not it? So 2 pi, what our frequency? 50 hertz, right? So 50 hertz, we multiply it by our 50 hertz, and our inductance 0.1. This gives me what? 110 pi. Is that not it? Which is the same as 34.2 solve 10 pi. That's 31.42. 31 point. I have 31.42. So that is my reactance calculated, and that is an inductive reactance. The B is impedance. So impedance, this is what we call RL circuit. In an RL circuit, to find our impedance Z, Z is equal to the square root of what? Our XL squared plus R squared. So we simply have square root of 31.42 squared plus my R, which is what? 12 squared, right? So you simply put this one into the calculator. 31.42 squared plus my R12 squared. That gives 33 ohms, the total impedance. Then next is to calculate the current. Remember our source is 100 volts, right? So my current is simply equal to my total voltage over the impedance. 100 over 33.63 then becomes my answer. So 100 over 36.63. And that is equal to 2.73 ohms. Now the phase difference. So the phase difference theta is equal to tan inverse of my inductive reactance over R as far as that. That will be 33 point. No, let me do it here. So tan inverse of 33.63 over my R, which is 12. So you punch that. Tan inverse of 33.63 over 12. That is 70.36 degrees. You realize that it is less than what? So 70 right here. 70. So this is all for calculating impedance. So we'll be solving more problems as we move along. And thanks for being with me in this video. See you in the next lesson as we go through how to calculate power in an AC circuit.